All right. Welcome, everyone, to the first session of the morning. So this talk, just make sure you're in the right place, is tools that enable data-defined and containerized testing of multi-service network systems. All right. An alternate title for this talk could have been, What This System Needs is More YAML. All right, but whether you love or hate YAML, hopefully you'll be able to get something out of this talk. All right, so just a brief intro about me. I started as a Clojure engineer when I was hired at LanoCloud in 2011. LanoCloud was acquired a couple of years later by Viasat. Earlier this year, I started at Equinix. I have a PhD in computer science. The topic of my dissertation was generative testing of browser rendering engines. Back in the early days, Chris Hauser and I did an early spike on trying to get Clojure script to be self-hosted, and then I did a presentation at Clojure West 2013 on Clojure script and Clojure script. I also created the Make-A-List project, the Mal language, and I've started some other open source projects listed there. But today, what I'm going to talk about is some different open source projects that I'm involved with. All right, so once again, this talk is tools that enable data-defined and containerized testing of multi-service network systems. So it's a bit of a mouthful, but hopefully as we go along, that'll become clear what I mean by that. The focus of this is going to be on the tools, but there are some high-level themes that are woven through the tools that I want to emphasize. So these tools are data-defined tools for testing and development. They're containerized, so they use Docker and Docker Compose, and they're written in Clojure for the most part. And by the way, there's a lot to cover, so I won't be taking questions during the talk. Hopefully I'll have a couple minutes at the end. But I do want to answer everyone's questions that you have, either in the Discord channel or in the hallway track, so make sure to get in contact. All right, so what is a data-defined approach? Basically, data-defined means that the systems put data in control, where the data drives the logic and the behavior of the system. So the question would be why? Why would you take that approach? From personal experience, what I found is that data-defined approaches lead to faster dev and test loop. There's less, like for example, less time spent in compile and build. There's greater interoperability and openness. And in particular, other tools, arbitrary tools, can consume and generate the data that's driving your system or coming out of your system. And it's easier to do testing and behavior simulation, especially when we get into like generative or property-based testing. And given the name on this conference, I thought I'd just show that in large part, Clojure could be considered a data-defined language, or Lisps in general, where the syntax is essentially data that defines the AST data structure that will be generated in memory. Another example of a data-defined tool is the clj-protocol library. It takes a data-defined approach to defining protocols, and it includes in the repo an example like DHCP protocol implementation, and that's this is the included example, and it sort of looks like it was pulled basically straight out of a standard spec document. And that's because it was, and then some metadata was added. All right, and then this is so the data-defined approach, we combine it with Clojure, and it gives you this really flexible and powerful way to quickly create binary protocol services, testing, mocks, shims, for arbitrary binary network protocols. And what I'm showing here is basically the 64 lines of code that use the clj-protocol DHCP definition to create a DHCP server. And this DHCP server has an IP pool backed by Postgres and sends events to NATs. All right, so what I'm showing here is a full system, demo system that I'm going to use to show the tools and the data-defined approach. So just a quick summary of this diagram. In the bottom middle is a data store. Right above that, we have horizontally and dynamically scaled app nodes or API nodes. Those have a load balancer in green above them that's distributing the load. Those API nodes, the way they scale dynamically is they use DHCP to get an IP address on the left there of the diagram. That DHCP server is actually what I just showed. The balancer, so the DHCP server also sends events to the message bus as those API nodes come and go. And then there's a component in the load balancer that listens for those events and updates the target config of the load balancer. And then there's a couple other things on the diagram. In the upper right is some blue boxes that are basically monitoring tools. Below that is some testing tools. And then in the upper left is a alternate configuration that allows us to do statically defined multiple API nodes without the DHCP dynamicness. All right, so this is a fairly simple system in a way, but it does have a lot of elements of what make production systems difficult to understand and develop and test and debug. So I'm going to use the system as a model to show how a data-defined approach can help with these problems. But even this model is a bit too much to start with, so I'm going to simplify it down to sort of the bare functional essentials. We have a data store, and then we have application logic in the API node. And the tester or user interacts directly with that. So how do we define this in a data-defined way? Well, the choice we've chosen, and most people do choose this at some level for these kinds of systems, is Docker Compose. And so this is basically our simplified essential system, simplified down and defined in Docker Compose, Docker Compose YAML file. So we've defined two services here. There's an API node. It builds from a directory, the code directory. It exposes port 8000 to the world. And then we have a DB service. This uses a generic Docker image for Postgres, sets some credential values, and then we mount in a volume that has our DB schema and some seed data. And these files are nearly data-defined, I would call them. One of the other features that Docker Compose has that you may or may not know about is something called override or overlay capability. And what this lets you do is combine two or more Docker Compose files, merge them together into a single configuration. So here's an example of a couple of Docker Compose files in the top left and top right. And essentially what Docker Compose does when the overlay capability is it basically does a deep merge. Although arrays are appended generally, and maps or dictionaries are merged normally. There are some special cases that Docker Compose does with the merging, but that's essentially what it does. But there are some pretty major limitations with that you'll run into if you start using this capability a lot. It can get pretty unwieldy when you have more than a couple files. And critically, there's no way to represent dependencies. So this compose file in the upper right, guess that direction. Compose file in the upper right, that compose file is not standalone. It won't work without the one on the left. And the reason is because the bar service there doesn't have either an image or a build definition. That comes from the one on the left. And so it has sort of an implicit dependency on the one on the left. Introducing a tool called MDC to solve some of those problems. Basically modular Docker Compose, manifold Docker Compose, you can pick the M. But what MDC does is it allows us to define groups of services as modules, and then we can compose them together. You probably can't see this real well, but what I'm showing here is 6 different modules that basically define the system that I showed, the demo system. And each module is actually a directory, and inside the directory is a compose file, and then other files that are related to the module. And also, critically, there's dependencies defined in each of those modules, the modules that they depend on. And so, might not be able to see the lines on the screen, but it'll become a little more clear when I show that, like if the user runs MDC, chooses the direct module, what will happen is it'll pull in the direct module, and then the transitive dependencies, so the API module and the Conlink module also get pulled in. And importantly, they get pulled in resolution order so that the merging happens correctly. If the user instead chooses the static module that does the static configuration of the API nodes, that will implicitly pull in the balancer module, and it will continue to pull in the API and Conlink modules as transitive dependencies. And then likewise with the DHCP module, this is sort of the full system, full dynamic system, and it's similar to the static one, but has the DHCP dynamicness. And what you're seeing on the right there is basically which parts of the system are selected when the user selects those MDC modules. So MDC gives us a way to basically do a data-defined approach to managing service groups and compose them together. However, one of the next problems you run into if you're using Docker Compose for this type of complex multi-service network testing is you'll run into limitations in Docker Compose networking. And so some of those limitations are that the default Docker Compose networking is basically layer 3 only. It's IP level. It has a pretty simplistic, flat view of the networks and the IP namespace, IP ranges. And you can technically define multiple networks in your Docker Compose and attach multiple networks to single services. But you don't have any control over what the interfaces will be named or the numbering of those interfaces, the order. And so Conlink is a tool that we use to solve the networking problem in Docker Compose context. So it allows you to define arbitrary layer 2 and layer 3 networking, routers, switches, bridges, the different broadcast domains and all that at the granularity you need. It has better support for dynamic containers. So Docker Compose does have a scale capability to set multiple replicas of services, and Conlink has better support for that when you want to use it with like user-defined IPs and MAC addresses. And one of the really important things that Conlink enables is an easy way to do network impairments. So you can easily add to any part of the system. You can add packet drops, latency delays, data corruption, packet reordering, that kind of thing. All right, so enabling Conlink is as simple as adding this service to one of your Docker Compose files. This is a normal Docker Compose service, but it has some elevated permissions. You can see the host PID namespace. It mounts in the Docker socket from the host so that it can watch for Docker events across the system. It can also coexist with Docker Compose networking, but generally I think when you're using this, you'll probably want to turn off Docker networking for all your services because we found it's important to have strong network isolation generally when you're like really wanting to test systems reliably. So this is what the configuration, a sample of what the configuration looks like in a Docker Compose file after you've added Conlink to your configuration. You can add configuration to your Compose file at the top level using the X network key. You can also add it down in a service, and it'll implicitly add the service definition. And you can also specify like your network config in a completely separate file if you want to have like separation of concerns with your networking from your service definitions. All right, so when we run MDC with the direct configuration, there's networking definitions in the direct module and also in the API module. And those basically get merged together. Conlink does the merging in sort of an intelligent way so that you can do like override or extend your network configuration with one module. So when you select MDC direct, this is basically the configuration that results, the composition of configuration that results. Likewise, if we do the static configuration, there's some more configuration that happens, and I'm just showing you what, like, if you extracted the networking configuration, what it would look like. And then here's the DHCP mode. All right. So what I mentioned earlier about data defined allowing sort of an openness to other tools being able to consume and generate and analyze your data. This is an example of that. There's a tool included with Conlink called net2dot. And what this does is basically it uses graphiz, or it generates a graphiz dot format from your Conlink network configuration. And so this isn't the prettiest layout that you can use with. So you can adjust this to get prettier layouts, but I just wanted to show that this is without tweaking any layouts or anything. It basically took that network configuration and generated a .graphiz file format from that. Okay, so before I get into some of the demo stuff, one more thing I want to talk about is a tool called dcmon. One of the challenges you have when you start using Docker Compose and have lots of services defined is that you're going to have a flood of logs that you have to analyze to figure out what the status of your system is. And so dcmon sits in that space where it allows you to basically, in a data-defined way, define checks that are going to run, and then you can have a visual display of what the status of the system is. So the top image here shows like if we're using the DHCP configuration and we run dcmon, and this is what it looks like when everything's up. All the checks have turned green. The bottom shows the data-defined checks. Most of the top 4 there are basically regex matches on the log output from that container. What I'm showing here is just the balancer, the checks for the balancer service. So we can do regex matching on logs from that service. It also has support for running a command repeatedly that will basically turn the check green when it exits successfully. All right. Let's do some demo. Oh my, okay, let's see, make sure here. Oops. Okay, good. All right. So I have a terminal split in 2 here. At the top, I'm going to run mdc direct. It selected the modules Conlink, API, and direct in that order. I am now going to start dcmon in this window, and it will wait for things to start happening. And then in the bottom, I'm going to use DC. DC is just a simple Docker compose wrapper for brevity, and start it up. All right, so you can see at the top, dcmon, the checks fired, everything came up. This is the simplest configuration, so there's not a lot of checks shown. But I can do a curl wrapper. This is just a wrapper on curl that formats JSON, and I'm going to query the user's endpoint of this service I just brought up. And so here there are two users that were seeded into the database. They're returned here. And now I'm going to do, oops. Guess I don't have it there. All right. I'm going to manually scale the API nodes up to 3. Oh, and I meant to have logging going, just so we can see activity. All right. So there are 3 nodes. Actually, yeah, there are 3 API nodes running now. They are not load balanced or anything, so I have to, when I query them, I have to do different ports. So I can go to third, and you'll see in the top the API 2 and API 3. You can see the request and the response going out. Okay, so if I, one thing I'm going to do is I'm going to post to the user endpoint to create a new user. And then I'm going to go back to API 1, and you can see that these API servers are using the same data store in the back because I have the user there too, visible there too. Okay, go to a new window, and I'm going to bring up a different Docker Compose instance. This one I'm going to configure with DHCP. Oops. All right, we'll bring it up. There's a lot more checks here, and like I said, this is dynamic. So we have DHCP. Those API nodes are registering with DHCP. Those events are going to the message bus, and the load balancer is picking those up and adding to the target configuration. All right. So now if I do start logging of that log, I'm tailing basically the log of all the different containers in the Docker Compose context. All right. So now I have a load balancer. I'm going to hit port 8000, which is balanced, hit the user's endpoint, hits API 1, API 2, API 1. There's only 2 currently configured. And one of the powerful things about this, that we have all these services running on the same host, is that we can do, the way Conlink works is all the Conlink configured network, all the traffic passes through the Conlink container. So all the bridges and everything is routed through or bridged through there. And so we have a single point where we can actually look at the network traffic, all the network traffic flowing through the system. So I'm actually going to run tshark in the Conlink container. I'm going to filter out transmissions, retransmissions, and duplicates because all the traffic hits here. There's a lot of in and out that happens, and so it's just noise. And then I'm going to listen for Postgres traffic and NATS traffic and DHCP traffic. So I'm going to basically just show like the back end control network traffic. All right, so I started that. And now I'm going to scale up my API nodes from 2 to 3. And what you're seeing down here, we see DHCP traffic, there's Postgres traffic, and there's also NATS traffic mixed in here. All right, so I just wanted to show that by using this system, you basically have like an omniscient view of all your events and network traffic on your system. And importantly, one of the things that this enables or gives you is you don't have timestamp skew because of your distributed systems. So even if you have a really good configured NTP system, you can still have some close events that can be hard to figure out the order that things happen. So this has been really powerful for debugging complex problems. All right. Let me. All right. Oops. Okay, so the next thing I'm going to show is I have a separate standalone configuration that's going to pull up the monitoring configuration. So this is a monitoring module I'm going to use, and I'm going to bring that up. This is Grafana, black box exporter to do latency pings, and Prometheus to gather that data. And so now I can go over here, and hopefully this is running. Excellent. Okay, so this setup is doing basically HTTP requests to both the simple system and the more complex DHCP configured instance. And so you can see latency here from both of those. It's in a few millisecond range. All right, I'm gonna go back here. I'm actually gonna tear this down. Not that one. I'm gonna tear my DHCP configuration down. And I'm going to add a module. Let me just show that real quick. So this impair module has a compose file, and it's adding to the transmit latency to the API nodes and the database node. I'm adding 10 milliseconds of transmit delay, and I'm also going to drop 20% of packets that arrive at the DHCP service. All right, so now I'm going to compose that configuration, and then bring things up again. Make sure everything comes up. It'll probably come up slightly slower because of the impairments. Okay, that wasn't too bad. All right, let's go back here and look at our Grafana dashboard. The direct one is still going along because I haven't changed that one, the same latency. By the way, this is a log scale graph on the left. And so what you're seeing here is the average latency, or the bottom base latency of the DHCP configuration has gone up in the 20 plus millisecond range. And then we have, because of the packet drops, we have these spikes in latency that are happening that you can see there. Okay, so just want to emphasize this ability to in seconds, basically, change the impairments on our system, bring up the system again, and be able to see what the impact is if we have these different kind of network problems in your system. This is something that is often pretty difficult to accomplish in like staging. Well, definitely in production it's difficult, but even in staging it can be difficult to replicate this sort of thing, and definitely not as fast. Dev cycle. All right. How am I doing on time? All right, great. All right, so the next data-defined aspect I want to talk about is testing. So there is the tool I'm going to talk about is Instacheck. So Instacheck is a library and a command line, and it provides a method of doing data-defined testing. And specifically the technique it uses is generative testing or property-based testing. So the generative testing model, rather than defining like individual tests in your system, hard-coded tests or fixed tests or even parameterized tests, what generative testing does is generate random tests against your system, and then verifies that those tests have the right behavior. And so what you're defining in generative testing is a way to generate those tests, and then you also have to define a way to validate those tests, because you don't know ahead of time what the tests are going to look like, so you have to have some way of validating it. And so in the Instacheck context, the way we do this is we actually define and generate tests using a formal grammar language called EBNF, Extended Bacchus-Naur Form. This is in contrast to the traditional approach of generative testing, where you're often defining like code generators that, a hierarchy of code generators that generate the tests. And then the other aspect of generative testing is how to validate those. And this is what's called the Oracle problem in the research literature. And it is a pretty big problem with generative testing. And so for complex systems, it can be sort of difficult to define, like to know ahead of time for any given random test what the behavior of the system should be. And so often if you're using this for a complex system, what you end up doing is defining a whole parallel model for your system that you can have a bit more confidence that it works, but you're always sort of have a little question there. So in this context that I'm showing, that demo system and the types of systems that this represents, there's actually a solution that sort of presents itself. And what that is that we often, when we're deploying complex systems like this, we have problems in production, right? With the scale and dynamicness, the logging, the asynchronous nature of the problem. And so, we will often, have a successful, when we're doing it in small, with our single Docker compose file, simplified system, we run tests against that, they work fine. We put it in production, and we see problems there, either the users or when we try and test it. If you have that kind of environment where you can test in production, you see the problems there. And so in that sort of scenario, we actually have an apparent answer to the Oracle problem, which is we'll just use the simpler configuration as the Oracle for the more complex system. All right, so this is what the EBNF grammar looks like that Instacheck uses. Again, this is EBNF, an EBNF document. And what this specific one is defining is basically it's going to generate JSON, a JSON list that contains maps. And each of those maps basically defines HTTP requests that we want to make to the system. So technically, this is actually an EBNF grammar for parsing a test. But what Instacheck does is turns this around and uses it to generate tests, random tests that conform to the grammar. And I'll just point out one thing. If you look at the IDs in the middle there, there's in green, there's some comments, but there's a special form of comment that allows you to adjust weights in the grammar. And what I mean by that is that when the generator comes to a point like this where it's generating an ID, this is sort of a logical or alternation between the 9 non-zero digits. And by default, Instacheck gives a weight of 100 to the different paths that it can choose. And what we're doing here is making 1 and 2 10 times and 5 times more likely to occur in your generated tests, respectively. And it supports inline weights like this. You can also define your weights externally in a separate data-defined file. And so this is basically the same weights that we're seeing in the comments, but this is the weights that I've extracted here. And so this is an Eden format. Instacheck can load these, so you can export the weights, tweak the weights to affect what your tests you're generating, and then use these weights in your next test run. All right, so Gentest is a program for this context that I wrote that wraps around Instacheck. And this is showing one of the commands that Gentest supports, which is just generate some samples. It's not going to do any testing, it's just going to generate some random samples. And I've showed a few of them here that it's generating. One thing to note about generative testing, if you're not familiar with it, is as you're running your testing, your test samples, the things that are generated get larger and more complicated as it iterates through and tries to break your system. And what this does is a really effective way of breaking or finding bugs in your system, because if you do enough iterations, you could have a 10 megabyte test file. And so the problem, though, is that 10 megabyte test file might trigger some bug in your system, but it's almost useless for testing and debugging. And so the modern generative testing approaches shrink your test. After they find a broken test, it will continue testing your system and trying to shrink that, basically simplify and shrink your test down to something simpler that still causes the problem. And Instacheck supports that shrinking process. All right, so I'm going to show this here. All right, I am going to restart my DHCP configuration without the network impairments. All right, and then did I bring it up? Yes. All right. Start logging the system. Oh, we're seeing traffic from our monitor. That's still up. Okay. All right. So I'm going to run gentest, the check command, and the two endpoints I specify here are basically our system we want to test and basically the test oracle, the simpler system. And I'm using a C just for demo purposes here, so I have a bit more predictable behavior. Because again, it is randomly generating tests. So there's no problem was detected. That was a successful test. It ran through 10 iterations, generating 10 bigger and more complex iterations. Didn't find any problems. You can see the request going by at the top. Run it again real quick. Okay. So there's no problems detected there. I'm going to tear this down real quick. I'm going to reconfigure it. And I'm going to add a module that introduces a synthetic bug into the system. Just wait for things to come up here. All right, now I'm going to run that same test again. I'm going to run the same command. It'll be different. Well, actually, it will be the same initial iterations. Actually, I want to be logging here. Let me run that again. Just so you can see there's a lot of output that'll go by, and what happened was it found a bug in the system. It found a divergence between our simple system and the more complex system, and this is right here. Here's the test that it initially found that caused a divergence. And then it continued to run and found a bit smaller test here. So that final shrunk test is here. This is what when it was doing this to both systems, it found some divergence with this test. And so let's see here. I am going to use another command called parse. So I'm going to feed it back in. So what I'm going to do is basically get Instacheck to go in the normal parsing order for parsing grammars, and parse this. And what parse outputs is actually the weights, or a weight format. But it's not actually the original weights. What it's showing here is these are actually counts of the number of times that this path through the grammar was traversed in order to parse that test. And so what we have here is basically a weights file that we can use this with Instacheck. So we can use this weights file with Instacheck, gentest, as the weights. And what will happen is you'll generate probabilistically similar tests to the one that you found the bug with. And this can be really useful when you're doing testing and debug to have similar things but slightly different that trigger the same underlying bug. I mean, it may not, and another interesting thing you may get out of it is, as it generates a slightly different test, it doesn't fail, and that is also useful information when you're debugging. All right, one more thing I'll show here is the parse command also supports an eBNF output option. So I'll run that. It'll parse the sample, and then it outputs the weights, but it also outputs a new eBNF file. And what this is it's a smaller version of the original eBNF file, but anywhere where the weights are 0, i.e. that path through the grammar was never traversed, those parts of the grammar are pruned out. And so what we're left with is just the grammar that can generate those tests that Instacheck found as a failing case. All right. doing on time? All right, great. All right, so that was data-defined testing. Another aspect that we want to be data-defined is not just the generating single tests or single categories of tests, but also test suites. And so for that, we have a tool called dctest. I'm actually going to go over this briefly just so we hopefully have time for a few questions at the end. But this gives you a taste. It gives you a taste of how we define suites of tests. It's a fairly young project, so there's still a lot of changes in development and features that we're working on the roadmap. But this is sort of like the vision is that we have data-defined test suites that we can use. All right. So there are some tool limitations. I'm not going to go through all these, but another way of looking at this screen is this is like an invitation to get involved and improve these tools. A lot of these are all in progress. They're not done, and so I'll just skip over that to the final slide. So here are links to this presentation, the demo system that I showed, the different projects that we're working on. And I do want to give thanks to the other active contributors to this project. Aaron Brooks is with me at Equinix as a collaborator on these tools. And at Viasat, John Smock and Norman Suarez and Greg Warner are also active contributors to these different tools. So I just want to say thanks to them for all the good work they're doing. And thank you for attending, and I can take a few questions. Yes? How did I derive the oracle? Yes. Well, like I said, the oracle is just we're just using the simplified system as the oracle.
Minimize the number of API nodes and things like that. Is that the way you got it?
Yeah, that simplified system that I showed had just an API node and just the data store, right? So that has the functional essentials of the system, right? It doesn't have all the extra, the scaling, the horizontal scaling and other dynamic aspects or monitoring that's causing noise, that kind of thing. And so I used that as the oracle. So what it's doing is comparing the simple system and the behavior of the more complex system, and divergence means we have a problem. Yes?
With Conlink, do you find you want to change the network behavior without sort of tearing it down and bringing it back up, sort of thing, right? Like if you wanted to mess with, tweak latency or something like that while the thing is running, do you ever find a need for that?
Yeah, so the question is, in Conlink, can we do dynamic impairments, basically, without tearing the system down and bringing it back up? Not currently. That is something that we've talked about and is on the roadmap for doing dynamic impairments with Conlink. So you're not prevented from doing dynamic impairments, though. If you go into the Conlink container, you can use tcqdisk netm to apply impairments the same way Conlink does.
So that's what you're using.
Yeah, it's using the netm module of tcqdisk to do those impairments. Other questions? Yes?
Have you explored using YAML script as an alternative to specialized algorithms for merging YAML files and such?
So the question is, have I thought about using YAML script for doing the merging instead of using the specialized algorithms?
Self-generating YAML or whatever it's for.
Yeah, I actually am familiar with YAML script. I haven't really. We have looked at other alternate ways. I think eventually we're actually going to have to get away from Docker Compose's overlay and override capability. There's some rewriting of the Docker Compose file that we want to do, I think, in the future. I haven't explored YAML script for that purpose. I'll have to think about that a little more, but yeah, it's. It is nice to be able to use Docker Compose's overlay because people are familiar with it. But yeah, there's more that we want to do, and I think it's a little bit limiting at the moment. So. Other questions? Yes?
Can any of this be useful in Kubernetes world?
Yeah, excellent question. So the question is, can any of this be used in the Kubernetes or Helm world? I think there are paths towards that, and we have thought about that. How would we cross that divide? I think the main challenge is actually with Conlink, because it does rely on having all the parts of the system on a single node. And also Kubernetes uses CNI networking rather than the networking that Docker uses. And so we've talked about and explored the possibility of creating some sort of CNI plugin for Kubernetes that would allow us to do the Conlink type stuff. But I think that's one of the main blockers. So we've thought about it, we haven't done it. So contributions welcome. All right, anything else? I think we're at time. So thanks again. And like I said, if you have questions, more questions, please come see me or ask on the Discord channel. I'll be happy to answer them.